Last time we were talking about computerized layout planning, and the focus of the last two lectures has been on the development of process layouts. In today's class we are going to talk about the design of product layouts or assembly lines and the features that are there in product layouts. If you recall, we had talked about the PQ chart, and in that we had identified the range in which product layouts and process layouts are used. Let us briefly recall the features of these different kinds of production systems and see which kind of layout is relevant under what circumstances. For instance, when you talk about kinds of production systems, we can talk about a flow shop. A flow shop is essentially a production system in which the same set of operations is performed in sequence repetitively. So what we have is essentially when the operations are going to be repeated so that the pattern of flow of the raw materials through the plant is constant, more or less. That particular configuration is called a flow shop, and in fact such systems, even an assembly line could be viewed as a flow shop in that sense. On the other extreme, we can talk about a job shop. A job shop is something where the facilities are capable of producing many different jobs in small batches. So the difference between a job shop and a flow shop is essentially in terms of the variety of products that are handled. In a job shop you can handle a variety of products, and because each product might require different kinds of processing depending upon its requirements, you have actually general purpose machines laid out in the job shop, and each product can go to the respective machine, get the operations done, and then go to the next particular machine for the new operations. So what really happens in the job shop is that the flow pattern is quite complicated, material handling costs are pretty high, and basically when you are designing layouts for such job shops, you are basically talking about the design of process layouts, and what we are talking about is designing a process layout which can accommodate the variety of products that you make, and that is what we saw when we were dealing with both the systematic layout planning procedure of Muther and also the computerized layout planning packages which are there for handling such types of systems. Of course, one can have a production system which is totally distinct and which is a project which would be a major one-time job requiring sequencing and coordination among interrelated tasks. Now in a project, therefore, things are done once and for all, and there is no need for repeating whatever you are doing. Generally a project is a one-time activity, and therefore whatever layout emerges is actually a layout dictated by the particular circumstances, and therefore there are no formal methods of designing a layout for a project. It is actually dictated by the various activities which have to be performed in the project, the kind of equipment that is to be laid, and the kind of terrain in which the project is to be done. So we are not really talking about layouts when you are talking about a project for these reasons. Now it is important to note that all these different kinds of production systems that we have talked about essentially require resources, and let us recall, these resources could be manpower, machines, materials, money, energy, information, etc., which have to be provided to the production system, and the production system will generate for you the desirable goods and services, and also some undesirable goods and services in the form of pollution, noise, scrap, etc. The purpose of a layout is actually to facilitate this operation which goes on within the black box. So we should look at a layout as something which facilitates the production process and at the same time tries to improve the productivity of the production system by and large. So it has to be viewed in that integrated concept and not a problem merely in isolation. This particular diagram, which shows a plot of the product variety versus the quantity, in fact brings out very beautifully the natural domains of the flow shop, the job shop and the project. For instance, if your quantities are small but the variety is large, then this particular domain is the domain of the project and the job shops primarily. On the other hand, when you increase the quantity and also relatively reduce the variety, in fact what happens here is that we are talking here about predictable variety in a job shop, and medium level variety and medium level quantities is actually the domain of the job shop. And when you are talking about the job shop, you are primarily talking about the process layouts, the design of process layouts. So whatever we studied in layout planning was actually applicable to the job shops at this particular end of the spectrum here. On the other hand, if we have a situation where the quantities are large and the variety of the product is relatively low, we come to a domain that is naturally suited for a flow shop or an assembly line or mass production, in that sense, where we are basically performing the same set of operations repetitively without much change. So in such a case, you tend to use a layout which is generally called the product layout, or we'll see how assembly lines are designed for this kind of. So I think this point ought to be kept in mind, that depending upon the natural requirements of variety and quantity, you choose the type of layout, and it could be a process layout or it could be a product layout as things are there. We are all familiar with the concept of mass manufacture these days and mass production. However, there are a couple of ideas in mass production or mass manufacture which are worthy of note. So we'll talk about some of the key ideas which led to mass manufacture as a viable entity. You all probably know that the first assembly line was set up by Henry Ford for making cars in the United States. But this could not have been possible unless you have, number one, a logical breakdown of work, which means the entire task which is to be performed is broken down into smaller and smaller tasks, and some group of tasks are assigned to one particular individual or a machine, and this breakdown of tasks into smaller tasks helps in the division of labor to a very large extent. And as a consequence of that, I suppose you would know what is the basic advantage of the division of labor. Rather than one person doing all the jobs involved in an assembly, if there are 10 people doing fractions of those jobs, what is the specific advantage that you get by engaging a large number of people?
Specialization of labor.
That's one thing. You get specialization of labor. That means individual people will now be focusing on individual tasks, and as a consequence they would become more and more skilled, and the learning times will tend to drop. I mean, their operation times will tend to drop. That is true, but that's not the real advantage of the concept of division of labor on which the assembly line is based. What is that specific concept? The major advantage of the division of labor is the fact that it is much more economical to produce parts when different people do the jobs. Why is this so? Because different tasks involve different degrees of skill. So what would happen is that there would be many tasks that can be performed by an unskilled operator. Other tasks require skilled operators, and you can buy an unskilled operator at a much cheaper rate as compared to a skilled operator for whom you will have to pay that much. However, if you had one skilled operator doing the whole job, then even for the unskilled jobs which he is doing, you are actually paying him at the rate of the higher rate. That's what it is. So you are really underutilizing his capabilities if you are employing only one person for doing all the jobs. This particular fact is in fact responsible for much of the economic advantage that you get through the division of labor. Apart from this, of course, there are other factors like development of a skill and these kinds of things, but I think this must not be lost sight of. The second underlying idea in mass manufacture is that it is possible to divide the work into workstations. What is a workstation? A workstation will be a set of tasks. You have now broken down the original work into smaller tasks. Some of the tasks are grouped together and assigned to one particular workstation. So at one particular workstation, maybe the operator will take the part, will inspect it, will fix up a component on it, and then clean it with compressed air and send it to the next operation. So he has performed a number of different tasks. So this grouping of what tasks are to be performed by the operator defines the content of a workstation. And basically Adam Smith was responsible for the basic idea of the division of labor. He wrote a book called The Wealth of Nations in 1776, which was basically concerned with the advantages of the division of labor. And Henry Ford was accredited with the first person who actually put these ideas together and developed the first assembly line. And of course, assembly lines would not have been possible but for this very important contribution by Eli Whitney. Have you all heard of Eli Whitney? Eli Whitney is the person who actually talked about the concept of tolerances and fits in mating parts. So he in fact showed that if you maintain the tolerances with a certain range, you could have parts which are interchangeable and replaceable. Now this is something very fundamental to the assembly line. For instance, if you look at the assembly of, let us say, Maruti cars, the person who has to fit the 4 tires onto the on the wheels of these this particular car, he can pick up one particular wheel, put it on, put the second wheel, put it on, third wheel, put it on. He can take any one of the wheels from the pile of wheels which is lying with him. Why is this possible? Because of the process of standardization that has taken place, which means essentially that dimensions conform to a certain range. Now, in fact, in all assembly lines this happens. The automobile is being assembled, he'll pick up any carburetor and fit up the carburetor on the car, and the next one he'll fit up the next carburetor, and so on. So it doesn't really make a difference which carburetor was fitted onto the whole thing. Whereas this kind of thing would not be possible if standardization was not there. You know, jocularly we can say, you have all seen the Mahabharata, and you know, whenever the during the war the chariot of particular prince was broken, they just couldn't replace the wheel by any standard wheel. It had to go to a specific carpenter. He had to make a wheel specifically designed for that and then put it on. He could not have a an off the shelf wheel which he could immediately replace. This is because that it was not a standardized kind of operation. Each thing was there. So unless standardization is done, you will not be able to go for this assembly of so these are three fundamental concepts which are at the back of mass manufacture. What is an assembly line? Assembly line is actually a very it's a sequential progression of the input material comes in at one particular point in one edge, and then it goes to the first workstation, and this person, it could be a person, it could be a machine, anything. This workstation performs certain operations on it, sends it to the next operator who performs those operations which are required, and so on. So at the end of the whole thing, the final assembled product comes out of the line. What are the specific features you see in the assembly line? I think one of the immediate things which comes to mind is that this production is going to be much faster as compared to a process layout. Why? Not because these machines are more efficient. I mean, the same machines could as well have been used in the process layout, so that the total processing time for producing a part would be the same. The only difference comes because in a process layout, it has to go from one department to another department. So there are waiting times, and then there is cost of transfer, and then it is waiting at the new workstation, and then so on. And once after the piece is finished, it has to again wait in the department. So all these loading, waiting, traveling is involved in the process layout. But here the part is some operation is performed on this part. Immediately it goes to the next machine, which is waiting for the part with open arms. It welcomes the part and starts performing the operation. So the element of material handling time involved is considerably reduced in these systems, and that is the reason why these systems are much more efficient in terms of production time. This is what it is. Here are some of the advantages of flow line production systems which we are talking about today. The first advantage is that smooth flow of material from one workstation to the next. You just saw that. But I just like to point out that this flow need not only be linear. You could have material flowing like this and then coming back like this and then going in this direction and then coming here. So it's a kind of a serpentine flow. Especially when there are constraints on space, you will find that this kind of flow takes place. If you see, for instance, any television assembly unit, probably go to LG or some other place, you will find that the operators sit like this and then sit like this and then sit like this. So they accommodate many more people, and this is also an assembly line. Moreover, the flow could be straight line, it could be U-shaped flow, it could be this kind of flow, or it could even be circular flow. The idea is that depending upon the space, but the crucial thing is that smooth flow of material from one workstation to the next takes place. So this is one of the features. Since work is fed from one station to the next, small in-process inventories result. This is another major advantage, because directly the piece is going from one workstation to the other. So there isn't much need for having in-process inventories between the two stations. Though of course there could be sometimes some inventories between the stations in the form of buffer stocks for some reasons. The total production time per unit is quite short for reasons that we just mentioned. There is reduced material handling. Little skill is required by the operators. Hence, training is simple, short, and inexpensive. Why? Because the operator is doing very, very simple kind of things, right? His job might be to pick up the piece from here, operate a foot pedal where it is held, and then take the compressed air and do some shoe, and then probably release it and send it to the next operation. So he has to do a couple of things which can probably be learnt in half a day. So training is quite simple and inexpensive, unlike the training for a process layout. In a process layout you might have a lathe operator. A lathe operator must have proper training. He should be able to read a vernier calipers. He should know how to operate a lathe. He should be at least an ITI trained person, and so on. So much greater problems there. In the product layout, production planning and control systems are simple. Less space is occupied by work in transit for temporary storage. Obviously, because we have lesser transit storage, so that kind of space is not really used up here. Whereas if you happen to walk through a process layout, walk through a foundry for instance, what you find typically castings are strewn all over the place, so you probably might not have space to walk through the whole thing. You have to mind your steps as you step from one casting to the other, and because of the storage that is there. Something like this would not happen, at least in a product layout. It would happen only at the end of the process layout. Of course, you will have a warehouse where all the cars are stocked, and therefore that's a different thing. Some of the disadvantages of flow line production are that a breakdown of one machine may lead to a complete stoppage of the following machines. Hence, maintenance is a challenging job here. This is a very significant thing, because if you happen to be in charge of a assembly line, you got to make sure that the line is running all the time, which means that if there is a request, if there is a breakdown, then maintenance staff has to be on the job constantly doing this job. This is relatively inflexible with regard to changes in product design. You cannot keep on changing the product design here. The pace of the line is determined by the bottleneck machine. Line balancing is thus a major problem in design. Obviously, if different operations, workstations take different amounts of time to process the part, the overall pace of the line will be determined by the slowest machine, and therefore you would like to have, as far as possible, fairly constant times for all the sections, all the workstations. This may not be possible for various reasons, but at least that's the intention. Supervision is general rather than specialized, as the supervision of a line is looking after diverse machines on a line. Compare this with the supervisor for a process layout. If you have a supervisor, let's say in the lathe section, that person would probably have spent 10 years in the lathe section and would be familiar with all the machines. He can probably open out each machine and assemble it, that kind of thing, because all are lathes and he has considerable experience. But this would not happen here, because you have one lathe, one milling machine, one some special kind of machine, and so on. So all machines are distinct in the line, and you don't expect any person to be a specialist of all of them. Generally, high investments are required owing to the specialized nature of the machines and their possible duplication in the line. So this is also possible here. Now, having understood the features of an assembly line, let us see, for instance, when to go for mass production. Incidentally, you must understand that this decision is primarily an economic decision, right? So just for the sake of argument, you might say, for instance, that suppose we have three options. We can either purchase the part that we are interested in making for 10 rupees a piece and just keep buying it, that's it. Or we can invest 10,000 rupees and set up some general purpose machines or individual stations, as the case may be, and then we'll be able to take a part on our own for 5 rupees a piece, and the total cost will then, the fixed costs and the variable costs will be of this nature. Or you might say that I can make a heavier investment of 20,000 rupees or whatever it is, it's only, and then maybe we can produce a part for 2 rupees 50 paisa per piece, and it will be like this. Now through a break-even analysis, simple break-even analysis, for instance, you can find out these two quantities, quantity Q1, quantity Q2 here. This is very simple. For instance, in this particular case, what would be the break-even quantity here for this particular situation? I mean, what we are saying is, what would be the break-even quantity here? This is like trying to say 10x is equal to 2000. So what we can therefore say is that we can directly determine this quantity. Let's call this quantity as Q1, and which is, let us say, 2000 here. And then you find out the trade-off between the other two options, that is between the option of buying at individual stations and the option of setting up a full assembly line. So what would be this value? 4000. So this Q2 is 4000. Now this simple analysis tells you something very interesting. What it says is that the least cost option is the one which is shown hatched here, and therefore if your demand happens to be in the range of up to 2000 rupees, it's better to just buy the part from outside. That's the cheapest option for you. If you happen to be in the range of 2000, your demand happens to be in the range of 2000 to 4000, the best thing would be to go on for this intermediate option, because it will be cheaper in this case. And it would be worthwhile to set up an assembly line only if your quantity of product or their demand happens to exceed 4000 rupees. That's what it is. So you can get quantitative answers to the question of finding out what would be the best thing to do under various circumstances. So in this particular situation, we would go in for an assembly line only if 4000 is it. What might happen in real life is that suppose your current demand is 3500 and you are somewhere here, whatever it is. Then obviously you can think of the future, and maybe if you envisage that you are expecting a growth in the next year, it might be worthwhile to set up an assembly line considering the fact that you are going to cross this barrier of 4000 in the next year, and so on. So these kinds of decisions actually have to be taken before you make this decision of trying to find out whether you should go for mass production and when you should go for mass production. So it is essentially an economic decision. Let's now talk about the design of the assembly line. What's the objective in the design of an assembly line? It is basically to minimize the total idle time or the number of workstations for a given assembly line speed. That's what we are trying to do. And the basic information that we have at our disposal in such a situation is that we are dividing the work into parts, and this division is known as the precedence diagram. So the precedence diagram is basically a projection of what are the parts that have to be, what are the components or the parts that have to be done in the overall product and in what particular sequence. Once we have done this development of tasks, the basic design of the assembly line is actually done by grouping the tasks into workstations. Before we do this exercise, we have to know what is the feasible range of cycle times, and the feasible range of cycle times we will see through an example can be determined very easily as something which lies between the maximum time for an operation and the sum of the times for all the operations. And then there are many algorithms available for the line balancing process. We have a procedure due to Helgeson and Burney, which is quite common, known as the ranked positional weight method. We also have a procedure due to Kilbridge and Wester, which is based on the number of predecessors. That means priorities are decided based on the number of predecessors. There is a procedure due to Arcus called COMSOL, which is computerized method for sequencing operations on assembly lines. The basic philosophy in this procedure is the generation of alternatives by simulation, and once you generate a large number of alternatives, you evaluate them and take the one whichever you think is best. Once we have generated a large number of options, the next stage is choosing the best design. Choice of the best design obviously depends upon things like balance delay and idle time for the operation, which should be minimum. So this is how this is the broad sort of picture of how the assembly line design proceeds. Let us now take an example. What we have here is a precedence diagram, and the precedence diagram shows that 1, 2, 3 and so on up to 12 are the individual operations or tasks. We are assuming that these tasks cannot be further divided, right? This could be drilling a hole. So obviously drilling a hole, you would not like to divide that operation into drilling 1/4 of the hole and then drawing the next quarter of the hole. So this is that one particular operation which is indivisible. So we have divided the entire task into these 12 operations, and this network diagram shows the precedence requirements. That is, operation 1 has to be performed first, and then 2 and 4 can be performed. Similarly, 6 can be performed only when 3 and 5 are over, in that sense. And the figures here refer to the duration of each task. So the duration of the task could be determined by a time study or whatever other procedures you have, so you know the times required to do these individual tasks. So from this we would like to possibly design an assembly line. So let's see how we can design an assembly line manually for this operation, and then we'll compare it by using the ranked positional weight technique. Now clearly in this particular case we are going to group these operations. So one thing is clear: what is the maximum time that is required for any operation? That is 7. And what is the minimum, what is the total time required for all the operations? That would be the sum of the times of all the operations, which is 50. So which clearly means that any assembly line for this precedence diagram will have a cycle time which will range between 7 and 50, right? So this defines the limits on the cycle time for any design. So in this particular example, the number of work elements is 12. The cycle time will lie between T max and summation Ti I is equal to 1 to n. So 7 is the bottleneck operation, the operation which takes the longest time, and the cycle time will therefore lie between 50. So this is important to find out that now you talk about a desired cycle time. Let's say that we want to desire, the desired cycle time must be somewhere between these two operations, between these two limits. So let's say our desired cycle time is 10. How does the desired cycle time come about? It is based on the market demand. It depends upon how many you want to produce per day. So cycle time is determined accordingly. So this is something that the marketing people would be actually telling you. There is a demand for so many cars per day, therefore your cycle time should be such. So we say that the desired cycle time is 10 and we have this. So this cycle time should be within this range. Obviously, if the cycle time happens to be more than 50, what is going to be the implication? The implication is that you don't require an assembly line, isn't it? Your cycle time happens to be more than 50, it really means that you require a piece, let's say in 60 minutes. So what you can do is, you can engage one person, he will do all the tasks in 50 minutes and still have 10 minutes free with him. So you don't really need to set up an assembly line if you are in this particular range, right? And you can use that person for 10 minutes, he can do something else. आपके टांग दबा सकता है, आपको कहीं ले जा सकता है, whatever it is, right? So you don't need here. On the other hand, if your cycle time is less than 7, what are you going to do? Suppose my demand is such that I need a cycle time of 5 or 3. That's right. So on this side you need multiple lines, On this side you have one line, and beyond this you don't need any assembly line. So it gives you a clear idea as to when you need how many lines in that sense of the term. So let's take for this example a situation that the desired cycle time is 10. Okay? So this is now feasible. It should be between 7 and 50. Let's now try to find out or design the line for us. What we are basically trying to do, what's the objective? This is the objective. Our objective is to group the work elements into stations so that no station time exceeds 10 units. That's what we're trying to say. Because if it exceeds 10 units, our cycle time will be more than 10. And we are designing the line for a cycle time of 10 units. How do we attain this? We could do it by inspection. Nothing, no algorithm, just look at the precedence diagram. And this is a feasible solution. What we can say is, I can club these two operations, 1 and 2, and this takes 5 minutes, 5 seconds or minutes, whatever with the unit of time, 5 plus 3. So the workstation 1 will take 8 units of time. I should not exceed 10, that's the important thing. So this is now 3 and 6, so this takes a time of 9. This one takes 4 plus 5, which is 9. This takes 2 plus 4, which is 6. This takes 6 plus 4, which is 10. And this takes 7 plus 1, which is 8. So what I have been able to do is, by simply grouping parts, what is the objective in grouping? That in the grouping, the sum of the times must not exceed 10. So I have 6 workstations. What is a workstation? I have exactly defined what is to be done at this workstation. That means the person who is going to sit at workstation 1 will first do operation 1 and take 5 minutes, and then do operation 4, which will take 3 minutes, thereby taking a total of 8 minutes here, and so on for the next operator and the next operator. So I have a design of an assembly line which has 6 operators, and we exactly know what each operator has to do. So this is basically the idea of an assembly line, which we just did by a simple common sense logic, which we can do it this way. However, to evaluate how good this design is, we would need some performance measures.
So if we want a cycle time less than 7, then instead of having a parallel assembly line, can't we have 2 machines or at operation number 12, so that the effective cycle time or the effective time becomes 3.5 at that operation?
Yeah, that is also a possibility. That is, you can have, for instance, if this is the bottleneck operation, you can have 2 machines here in parallel, and each machine will have a effective time of only 3.5 from that point of view, and then your bottleneck will be maybe 6. This will be the 6, which will be the bottleneck. 6, right? So you can work that way also. Or you can look for a superior machine, which instead of taking 7 minutes will take lesser time, whatever is your requirement. So for this particular example that we just worked out, we can calculate something called the line efficiency. What is the efficiency of this line? And this is nothing but the summation of all the station times, and summation of the station times will be nothing but the total time for all the jobs. So you have 50 divided by k. K is the number of workstations. The number of workstations that we have got is 6, into the cycle time of the line is 10. Notice that the cycle time need not be always 10, because when you are doing this grouping, you are constrained by saying that this should be less than 10. So just as we had got lesser values here, suppose this value had been only 8, then our cycle time would have been 9, although we started to design a line for a cycle time of 10. Okay, so we have here 10, and then of course the line efficiency works out to 83.3%. 1 minus the line efficiency is called balance delay, It's a measure of the inefficiency of the operation really. So it's a measure of the idleness of the different stations. When we talk about idleness, what do you see? Out of the total of 10 minutes, this guy is idle for 2 minutes. This is idle for 1 minute, 1 minute, 4 minutes. This is not idle at all, and he is idle for 2 minutes. So we would like this idle time to be as small as possible. An ideal situation would be when the line is perfectly balanced, that everyone is doing the same amount of tasks. But that is generally not possible. Why? Because the times are integral, number one, and then you have a constraint on precedence. You can't group everything into everything else. You are not weighing, for instance, rice, that you can put something here and make it exactly 250 grams. It's not possible to do that because you are dealing with these individual entities which have to be grouped together. Right. So the balance delay is 16.7%, and the smoothness index for this, smoothness index is a term for an assembly line which is nothing but this is the idle time, ST max, maximum station time, that is the cycle time, minus STI, which is the station time of the ith operation, and whole square. So it will be for each operation. So what we have is, look at this example, idle time here is 2, so 2 square is 4, here it is 9, so it is idle is 1, 4 plus 1 plus 1 plus this is 16, because the idle time here is 4. 4 4s are 16, no idle time here, and 4. So root of 26, which is 5.09. And closer to 0 the better. If a line is perfectly balanced, this smoothness index will be 0. So we try to minimize the smoothness index. So we have got measures of efficiency of this design. We've got a line which has an efficiency of 83.3%, a balance delay of 16.7%, and a smoothness index of 5.09. This is what we have. Now let us see how we can use one of the standard procedures available. We will discuss the so-called ranked positional weight method for developing the line, and we will compare that design with the design that we had obtained by intuition as it was. So the positional weight of a work element is its own processing time plus the processing time of all the following work elements. So we define a positional weight for each element in the precedence diagram by saying that this is the time of that operation plus times of all operations which follow it. So the basic idea would be that the total positional weight will give you an idea of how much time it will take at least to go to the end from that operation. That's the idea. And this is used subsequently in defining your priority for assigning jobs to workstations. That's the only thing. Okay. So at each workstation, a list of eligible jobs is prepared for placement. And in the ranked positional weight technique, the work element with the highest positional weight is selected. That's why it's called ranked positional weight. Is selected and is assigned to the current workstation. So that's the basic logic of the RPW technique. Let us try to apply this technique to the example that we were considering earlier. What you notice in this precedence diagram is it's the same precedence diagram that we had. The times are shown on top of each operation, but the figures that are available in the squares at the bottom are the positional weights. Now let's look at them. You start calculating the positional weights from the back. So what you see is for operation number 12, the positional weight is 7 because this will take only 7 units of time. You come to 11, then from 11 the time, this is the operation and this is the following operation for this. So 7 plus 4, 11 will be the positional weight for this element. Similarly 13 is the positional weight for this element, which is 6 plus 7. Similarly for 9, the positional weight will be what follows it, which is 7 plus 1, which is 8. When you come to job number 6 for instance, what happens? It is not necessarily 15 plus 8 plus 15 that will be the positional weight for this. That's the point that you have to get. It is all these jobs are successors of this job. So the time required 2 plus 6 plus 7 plus 1 plus 4 plus 4. The total time required for all these jobs is 24 if you add the 5 also, and therefore this becomes the positional weight for this particular job. For job number 3, the positional weight will be simply whatever follows this plus, so 24 is the positional weight here, 24 plus 4 which is 28. Similarly here it's going to be 24 plus 6 which is 30, 30 plus 3 33, 31, 28 plus 3 is 31, and when you come here it's not the sum of these two, obviously it is going to be the sum of all the jobs which come plus 5, so the total positional weight is 50 here. So the numbers that we have computed here can be computed in one run, starting from the back and coming to the front and getting these particular numbers. Now these numbers will define and will actually tell us how to determine the entire how to go about designing the assembly line. See, designing the assembly line is now based on these numbers, and this is how it proceeds. For instance, you start with the first basket, which is the first workstation. You open the first workstation, and at the first workstation this is the only job which is eligible because it has no precedence relationships. So 1 will be put there, and the moment we put 1, we have consumed 5 units of time, and 2 and 4 are again candidates for placement. But out of 2 and 4 we will take 4 because it has a higher positional weight. So we will put 4 here, and once we put 4 here, 1 and 4 will consume a total time of 8, and we can go up to a maximum time of 10. There is no other job available at this juncture which can be accommodated within this, so we close this particular workstation with a work time of 8 units and proceed to the next station. When you proceed to the next station, this has been placed and this is also there. There are 2 jobs competing for placement in this particular workstation. This one 2 and 5, and out of these this one has a higher positional weight. So we take 2 and place it first. And when we place 2, then 3 can be placed also and 5 can be placed. But out of the 2, this will get a priority. So if it can be accommodated, it can be accommodated because the total time is going to be only 9. So you can put this. So you keep proceeding in this particular fashion, and you will keep on filling these baskets. The moment you cannot enter anything more into this basket, you open the next basket. So we now have the first workstation, the second one, the third one, the fourth one, fifth one, and the sixth one. So in this design too, we have been able to determine the 6 workstations and also the operations which had to be done at these individual workstations, and these are the cycle times. And since this highest cycle time is 10, that means this particular line will now operate for a cycle time of 10 as we had decided earlier. So what we can do is we can look up, we can try to evaluate this particular design. We can see, for instance, that the evaluation of the design by the RPW method, again the balance delay and the line efficiency are the same, because the balance delay and the line efficiency are determined by the number of workstations. And in this design also you get 6 workstations. In the previous design also you get 6 workstations. Theoretically, what is the minimum number of workstations? How will you calculate this? You have 50, which is your total work content, and your cycle time is 10. 50 by 10 is 5. Ideally, you can work with the theoretical minimum number of workstations as 5. But in the 2 procedures that we have just adopted, we could not sort of pack these individual operations into 5 workstations. So the balance delay is 16.7% for here, and the line efficiency is 83.3% in this particular case. However, if you look at the smoothness index, there is an improvement in the smoothness index. The smoothness index you find for this design, look at the idle times here. 2, 2 square which is 4, 1 square which is 1, 1 square which is 1, 3 square which is 9, 0 and 3 square which is 9. And this particular value, the square root of this is 4.9, which is an improvement on the earlier smoothness index that we have. That means this is a slightly balanced, better balanced line as compared to the previous one. So we can therefore look at the precedence diagram, and from the precedence diagram, depending upon the RPWs, that depending upon the positional weights, we can determine how to fill up these individual workstations and come up with a design, and subsequently evaluate the design in terms of the three major parameters: balance delay, line efficiency and the smoothness index for these particular situations. The question now is, what are the possible reasons for a high balance delay? What could be the possible reasons for a, you see, balance delay measures the inefficiency, line inefficiency, which means the degree of idle time which is there for the various operators. Some of the reasons for this are: number one, the wide range of work element times. This can happen, right? What can happen is, for instance, in your example, the work element times will not be constant for all the operations, right? So if all the work element times were, for instance, 1 each, or even smaller than this 1 each, then you could combine them into getting any operation time. But this does not happen. Some work element time might be only 1 unit, second work element time might be 12 units, and you have to take it as it is because the operations are not further divisible. Another possibility could be a large amount of inflexible line mechanization. What might happen in a practical design situation is that you already have a line and you already have a great degree of mechanization, so that you have placed some machines and certain stations which already perform a certain number of operations. So you are actually constrained by putting those operations at that particular point, although that might not result in the best balance delay. This could be another reason. And then indiscriminate choice of cycle times could also lead to high balance delays. What it means is, if you know that in our example that we considered, the feasible range of cycle times was from 7 units to 50 units. It's a wide range, isn't it? So you could attempt to do a line for a cycle time of, let us say, 7, or a cycle time of 10, or a cycle time of 15, or cycle time of whatever it is. So if you do that, then for different cycle times you'll probably not get the right kinds of, you might get high balance delay. And they are actually some of the reasons why you have high balance delays. Let us now look at some of the problems and prospects of mass production. You see, for instance, that one of the major problems of mass production is that the variable work element times. We have said we have designed the line based on deterministic times. But if an operator is doing, if there is a manual task, then it is quite likely that the task time is normally distributed with a certain mean and a certain variance. So sometimes the operator will take less, sometimes the operator will take more. So then you will probably find that there could be starvation for these subsequent machines in that sense of the term. So what is done is, in order to deal with this problem, sometimes what is done is that buffers are provided in between the tasks. So what can happen is, even if this fellow is slow or this machine is slow, this particular person can keep on operating from these buffers. So this is the variable effect of the variable work element time. And in fact, this problem of finding out the optimum buffer is an optimization problem. It's a problem which can be determined. Then there could be a breakdown at a workstation. So if there is a breakdown at a workstation, what will happen? Since the line is all connected, where there is a breakdown, there will be flooding of parts, and beyond that there will be starving of parts. All the other machines will be starving. So that is why you have to get back into operation as early as possible, and we said the maintenance staff has to be very quick. There could be multi-product lines. That means the same line can produce multiple products. This can happen. For instance, in Maruti Udyog, the same line can produce a Maruti 800. It can also produce a Zen, because what they do is they change some operation, something, and then it can be done. So designing multi-product lines means that you can handle the same thing. We can also talk about modular production and group technology, which is an alternative to assembly lines, which means that you can talk about grouping parts in a certain fashion so that you can achieve modular production and cellular manufacturing, which will try to capture the advantages of both product and process layouts. That's the basic feature of cellular manufacturing. And of course, automation and robotics have their role to play when you're talking about assembly lines. Many operations can be automated, and you can have robots perform many of the operations. Right? So typically, for instance, in automobile manufacturing, you find that robots perform this operation of spot welding of various sheets and components, so on. And then, of course, these kinds of things, we can also use FMS and SIM systems to perform and automate and program some of the operations that have to be done. Finally, let's try to summarize what we have done in this particular class. We have tried to look at the advantages and disadvantages of assembly lines or product layouts primarily. We have seen what are the basic principles involved in the design of assembly lines, and we found that the basic principles involved were things like division of labor and interchangeability of parts, which were contributions by Adam Smith and by Ellie Whitney, which help us operate the assembly line. And then we saw that the precedence diagram and market requirements of the design, these are the two major inputs you need for designing an assembly line. So you need the precedence diagram and also what is the desired cycle time, what rate you'd like to produce the part. And we would like to do the grouping of elements in a product layout. This could be done by various algorithms. We mentioned some of them, and we actually looked at the RPW procedure in some detail. We found that there were measures of efficiency like balance delay, line efficiency, and smoothness index for a line. And finally, we talked about some of the emerging concepts, which would be in the nature of multi-product lines, the provision for a buffer, automation, and worker empowerment. Worker empowerment is a very important concept, especially originally given by the Japanese, which allow the operator to run the line at his will. That means he can stop the line when there is a problem. All the workers get together and they repair the line, and then they go back to their respective places and run the line. So these are some of the concepts which are there for product lines. I think with this we have been talking mainly about the strategic aspects of design of a production system in this course. Now we'll go over to the operational decisions which are relevant in a production system. That means we'll talk about the problem of forecasting, aggregate production planning, and planning a production system. Thank you.